Hi everyone, welcome to this session. I am Mohammad Shanoob, student of 3rd semester MSc Chemistry from E-Content Development Center, Majlis Arts and Science College, Puramannur. The topic I would like to discuss with you is the Mossabauer Spectroscopy. You people are familiar with the names such as electronic spectroscopy, molecular spectroscopy, Raman spectroscopy, etc. The Mossabauer spectroscopy can more conveniently described by its alternative name, the nuclear gamma resonance spectroscopy. It was discovered by Rudolf Mossabauer in the year 1958. Later, he got Nobel Prize Award for this work. As the name suggests, nuclear gamma resonance spectroscopy, this is simply a gamma ray spectroscopy in which the transition between the ground state and excited states of nucleus takes place, or otherwise in Mossabauer spectroscopy a nucleus is probed or pierced using a gamma ray as exciting radiation, and hence an absorption spectrum is measured. The Mossabauer spectroscopy is based on the resonance fluorescence of gamma ray. The resonance fluorescence of gamma ray, what is that? When an emitter nucleus decays from its excited state to the ground state, it will emit a gamma ray. This is what we call the gamma ray fluorescence process. And this gamma ray is absorbed by another nucleus and which transit from the ground state to the excited state. And this phenomenon is what we call the gamma ray resonance. And these two processes together we call the resonance fluorescence of gamma radiation. Later we get a signal from here and which is detected by a detector also. The elements that are used in the Mossabauer spectroscopy are iron 57, tin 119 and iodine 129. The Mossabauer spectroscopy is done by using Mossabauer spectrometer. Very important topic, Mossabauer effect. What is Mossabauer effect? Mossabauer effect is simply the nuclear resonance absorption of gamma radiation where there is no recoil or where there is no recoil effect. That is, Mossabauer effect is the recoilless nuclear resonance absorption of gamma radiation. Mossabauer effect has been observed in somewhat 100 nuclear transition in 80 nuclides in nearly 50 elements. The Mossabauer effect has been provided valuable contribution to the field of earth, biological, physical and chemical sciences. Then we are moving into the basic principle behind Mossabauer spectroscopy. What is the basic principle behind Mossabauer spectroscopy? Just as a gun recoils when bullet is fired, here also the conservation of momentum requires for a free nucleus to recoil during emission or absorption of gamma ray. What is the recoil effect or the recoil of a gun? When a high energy particle is moving from a body which is at rest, the body feels a back-kick motion that it pushes backward. This is what we call the recoil of a gun or recoil effect. Similarly, here when a gamma ray is emitted from a nucleus which is at rest, the energy of the gamma ray E gamma must be slightly less than that of the natural energy of transition due to this loss of energy in the form of recoil or the recoil force experienced on that nucleus. But in order for other nucleus to absorb this gamma ray, the energy of the gamma ray must be higher than that of the natural energy of transition due to this recoil force experienced on that particular nucleus. In both the case, the energy lost to recoil, and hence nuclear resonance is unobservable here due to the shift in energy is too large to have a significant overlap between the emission and absorption spectra. Next, we have seen that the gamma ray emission and absorption that takes place in a free nuclei or atom where it experiences the recoil effect. Here the equation to find out the energy of recoil ER is equal to E gamma square divided by 2mc square, where E gamma is the energy of the gamma ray and m is the mass of the atom. But in solid crystals there is no recoil because they are in bound condition. Still some energy is lost due to recoil, but in that case it will be discrete packets called phonons. Here the relation to find out the energy of recoil ER is equal to E gamma square divided by 2mc square. Here the capital M represent the mass of very large particle. So the value of ER, energy of recoil, is very less here. Next we are going to check what we are done with this Mossabauer spectroscopy. In Mossabauer spectroscopy, iron 57 is the most used element. Here the iron 57 is not used as it is. Here we are using the radioactive unstable cobalt 57 nucleus, where it is decays into the second excited state of iron 57 by the K electron capture. That means the electron capture from the kth subshell. From the second excited state of iron, it decays naturally into the first excited state of iron. The energy of the second excited state of iron is 136 keV. Here it decays naturally into the first excited state and the energy of it is 14.4 keV. Here the transformation from the second or the transition from the second excited state to the first excited state is not of our use in the case of Mossabauer spectroscopy. What of our use is the transition from its first excited state to the ground state. During the transition from the first excited state to the ground state, it emits a gamma ray, that is gamma ray fluorescence takes place, and the other nucleus absorb this gamma ray and it transits from the ground state to excited state, that is gamma ray resonance taking place, and we get a signal from here and it is detected by the detector as I told you before. But what the condition here for the Mossabauer spectroscopy to takes place, the atom in the source sample must be of same isotope as atom in the absorbing sample. That is the condition here. Next we are moving to the parameters associated with the Mossabauer spectroscopy for chemical application. There are three parameters for Mossabauer spectroscopy, that is the isomer shift or chemical shift, the quadruple interaction and the magnetic hyperfine interaction. Here I am going to discuss with you is the very first two parameters, that is isomer shift or chemical shift and the quadruple interaction. Isomer shift or chemical shift. What is mean by the isomer shift or chemical shift? The ET value, that is the natural energy of transition value, is affected by the interaction between the nucleus and the electrons around it. This arises because of the different sizes of the nuclei in the ground state and the excited state. What is mean by the difference in their chemical environment? That is the unequal nuclear radii of the source and the absorber nuclei and the unequal electron densities of the source and the absorber nuclei. Now we are moving into the isomer shift of isolated iron 57 species. Here these two represents the ground state energy level and excited state energy level of isolated iron 57 respectively. But due to the difference in the or the change in the chemical environment, it shifted to somewhat different energy level. That means either it may increasing or it may decrease. Here I am showing the in the case of increasing energy level. And isomer shift is a shift and it means not splitting. Here what happens is the energy level is shifted to somewhat different position. That means it shifted. This is what we call the isomer shift or chemical shift. Since S electron wave function have their maxima at their nucleus, and the Mossabauer spectroscopy is associated with the transitions that taking place between the ground state and excited state of nucleus. That means the s electron density affects the isomer shift or chemical shift to a greater extent, but the changes in the p and d orbital occupancies affects the s electron through only a screening. Hence, it affects the isomer shift or chemical shift only to a smaller extent. And the changes in the nuclear radius that happens from when we are moving from the ground state to the excited state is delta r. That means if the value delta r by r is positive, the isomer shift or chemical shift is also positive. If delta r by r value is negative, the isomer shift or chemical shift is also negative. Next, we are moving into the second parameter of Mossabauer spectroscopy, that is electric quadruple interaction. It mainly arises due to the interaction between the electric quadruple moment of the nucleus and the electric field gradient. Nuclei in the states having a spin moment I greater than 1 by 2, having a spin moment value I greater than 1 by 2, having a non-spherical charge distribution. This non-spherical charge distribution produces a nuclear quadruple moment. Hence, in the presence of an asymmetric electric field, that is produced by the asymmetric electronic charge distribution, splits the nuclear energy levels, and the charge distribution is characterized by a single valued quantity called electric field gradient. If the charge distribution is in the form of a sphere, the value of nuclear quadruple moment Q is 0. If the non-spherical charge distribution have the shape of an oblate, the value of Q is negative. If the non-spherical charge distribution is in the form of prolate, the value of Q is positive. And then in the case of an isotope with excited state I equal to 3 by 2, such as in the case of iron 57 or tin 119. These excited states here split into two substates, and we get a two-line spectrum or doublet here. We can find out the magnitude of separation or delta here by using the relation delta is equal to EQV by 2, where Q is the nuclear quadruple moment value and V is the principal component of the electric field gradient. Next, we are moving into the last topic, that is the importance of Mossabauer spectroscopy. The absorption depends upon the electron density above the nucleus, and the number of peaks obtained from here is related to the symmetry of molecule. As a result of the whole, considerable structural information can be obtained from the Mossabauer spectrum that we get. I hope you get an idea about what is Mossabauer spectroscopy, the Mossabauer effect, the basic principles behind Mossabauer spectroscopy, and the parameters associated with the Mossabauer spectroscopy, that is isomer shift or chemical shift and electric quadruple interactions. Thank you.